Hello everyone, welcome to our discussion of this topic on transformation of graphs. It basically talks about when you have a seed function such as f of x equals x squared, then that original function can take different transformation, can take different forms within the xy plane. And we will be talking about how that function can be moved in the xy plane. That's basically the main topic behind transformation of graphs or transformation of functions. Okay, so that I can show you some of the fundamental graphs that we will be dealing with. One is what you see right now. Well, I have to, I guess, zoom in. So the square root function, the basic square root function, as you can see, is one of those main seed functions. And we will be talking about how this function can be moved within the xy plane. Another one of those main functions is the absolute value function. So we will be talking about transformation of that. Then, of course, the very famous quadratic function we will be talking, which is y equals x squared, otherwise known as the parabola. And we will be talking about transformation of this function within the xy plane. And of course, one of the main functions is the cubic function, which has this main form. Y equals x cubed has this particular graph, and we will be talking about how this can be moved within the xy plane. And we will be using the computer today as well, just because writing manually or sketching these manually may not give you the accurate picture of what this topic really is. So I'd rather go back and forth between manual drawings that I will do on this piece of paper and computer generations of the same graphs. Okay, if I may, let me remind you please that the way to study in this course is first skim through a textbook section before you watch the video or you attend the class. Then watch the video or attend the class and take careful notes. And then review your lecture notes while, as you do that, you solve the problems that you saw during the lecture, whether it's in the video or in class. Solve those problems on your own, as well as those problems that you see in the textbook. And solve them without looking at the solutions. And then compare your solutions with the ones you saw in my lecture or in the textbook. And then finally, of course, please keep up to date with all the homework and complete them by the due date. And of course, as we go through the course, review, review, review. Okay, so having said that, notice that this first function, we have, well, first of all, I should mention something about the vertical line the vertical line test. The vertical line test, because in this section we'll be talking about functions. So we should draw a distinction between what's a function and what is not a function. So if a vertical line intersects a mathematical graph, such as this one, at only one point, then the graph represents a function. Otherwise, it doesn't. So for example, this graph, certainly if you drop a vertical line, it will intersect it only at one point, right? So this graph represents, and the function associated with it, it represents a function. This equation represents a function. The same way with this absolute value function. This is the graph of the basic absolute value function, right? Y equals absolute value of x. So if you drop a vertical line anywhere here, it'll intersect the graph only at one point. So this y equals absolute value of x is a function. The same way it works with the quadratic function. If you drop a vertical line anywhere, it'll cross this graph at only one point. So this is a function. Although parabola, at least this one, is a function, but when we look at the conic sections in trigonometry, in Math 127, there is also a horizontal parabola. For a horizontal parabola, a vertical line intersects it at more than one point, so it will not be a function. This, the cubic function, or y equals x cubed, also if you drop a vertical line, it will intersect it at one point anywhere along its graph. Okay, so that's what vertical line test talks about. So now that I've shown you some examples of what is a function, what about something that is not a function? Okay, let me use this piece of scratch paper because it's not relevant to this section, but I want to give you an idea what we're talking about. So a circle is not a function, right? Because if you drop a vertical line, it'll intersect it at 2 points, more than 1 point. So a circle is not a function. Another example of an equation or mathematical entity that is not a function is an ellipse. So if we draw an ellipse, whether it's a vertical one or a horizontal one, it makes no difference. Let's draw a vertical one. Here's a vertical ellipse. Then a vertical line intersects it at more than 1 point, at 2 points. So this is, a circle is not a function, and ellipse is not a function either. Other examples of things that are not a function is an is a horizontal absolute value function. So if you graph the function x squared equals y, if you graph that, the x, not x squared, that would be x equals absolute value of y. If you graph this function, it'll be something like that. Okay? So once again, a vertical line intersects the graph of that, the horizontal, or this x equals absolute value of y function at 2 points, which is more than 1 point. So once again, this is not a function. Another object or entity that is another entity that is not a function, it's a hyperbola. Right? A hyperbola, you can draw a hyperbola like that, something like that, right? I'm just drawing a rough sketch. And once again, a vertical line intersects it at more than 1 point, at 2 points. So once again, a hyperbola is not a function, and we can do that using the vertical line test. And let me, so this is, we established that these entities, mathematical entities, are not functions. Are not so, and we used the vertical line test for that. Okay. So back to our section here. Then, talking about each of these main seed functions, such as the square root function, the general form of a square root function is that one. And let me box it like that. So if k is equal to 0, then you have square root of x, which ends up being that. If k is some positive number, say 2, then x minus square root of x minus 2 moves the original square root function k units or 2 units to the right. Notice if k is positive, this square root of x minus k is preserved. That minus algebraic sign is preserved. So you'll have x minus something. And that means k, the original function square root of x is moved k units to the right, because k would have been a positive value, even though the algebraic sign stays negative. But the movement, the shift, the k shift is to the right horizontally so many units, whatever k represents. But if that algebraic sign becomes positive, so this is the main function. But if that becomes positive, that means what? That means k must have been a negative number, which means the original seed function square root of x, it moves k units to the left, because k must have been negative, which indicates movement horizontally to the left. Okay, that's when this algebraic sign becomes positive. If you have the original function plus some h outside of the square root, not inside like k, but outside, that indicates vertical movement up. So plus h represents moving the original square root of x function h units up, and minus h represents that movement, moving square root of x function h units down. Okay? If you followed what we discussed here, it's exactly like that for all the upcoming functions, with the exception that the function itself looks different, and it should be, right? It should look different because it's a different function. But the rules stay the same. The shifting rule, the transformation rules stay the same. For example, in this case, we have y equals absolute value of x minus k as the main general function for the absolute value function. So if k, so which means this function moves the absolute value function x k units to the right. Notice that this is it stays minus k because k is positive, so movement is horizontal to the right. But this algebraic, if k is positive, this algebraic sign negative stays negative. Now this one, if we have y equals absolute value of x plus k, that indicates k must have been negative, because this is the original, this is the general absolute value function. So if the middle algebraic sign turns positive, that means k must have been negative, because minus would be positive. So that means if k is negative, that indicates that absolute value function x moves k units to the left, horizontally to the left, because k is negative. Here, absolute value of x plus h on the outside of the absolute value means that the absolute value function is moved h units up, and if it's minus h, it means the absolute value function x is moved h units down. Okay, so I hope you're seeing the similarity between how the general function for each type of function, square root, absolute value, is connected with the way the transformation or shift of a graph occurs. Okay, it's the same rule. The function is different, but the rules are the same. Okay, so on this page we have the quadratic function y equals x squared. So once again, this is the general equation for a quadratic function. So it's x minus k, k being representing the number that will indicate how much horizontally this graph should be moved. So this function moves x squared, or this function, k units to the right. So depending on what k is, the movement happens to the right because this algebraic sign stays negative. That means k must have been positive. So if k is 5, this would be x minus 5 squared, and this vertex here would move 1, 2, 3, 4, 5 units to the right. By the same token, if that algebraic sign changes to positive, then this function moves the x squared function, which is this overall function, k units to the left. Because if that algebraic sign changes to positive, that means k must have been negative, right? So movement to the left, towards the negative side of this x-axis. If x squared is, if an h is added to the original x squared function, then the graph of the quadratic function, this, moves h units up. So if this is x squared plus 2, then this vertex moves 1, 2 units up. If it's x squared minus 2, this vertex moves 1, 2 units down. Okay? The cubic function, once again, this is the main general cubic function, x minus k cubed. Now this function moves x cubed k units to the right, because this algebraic sign staying negative means k must have been positive, so movement occurs horizontally towards the positive x values. And of course, if k is 0, then this will be x cubed, which is the function you see here, which represents this graph. Okay? Now, if that middle sign changes to positive, that indicates k must have been negative. So x minus something, or x plus something, let's say k is negative 3, so minus 3 would be x plus 3. So a positive operation in between these two means movement horizontally to the left, because k would have been negative. If h is some value on the outside of the cubic function added to it, that indicates that the function x cubed is moved h units up, and if it's minus h, that means the function, cubic function x cubed, is moved h units down. Okay? Having said that, let's go through some examples. I've already mentioned that a lot of mathematics is visual, and I'm sure you'll agree with me in this case, because we'll be going through a lot of graphs today. Okay, so given the functions and their graphs above, or below actually, sketch the graph for each of the following related functions. So this is correct. So this refers to what we talked about above here, the absolute value function, the square root function. So given what we talked about, these functions and their graphs, like that, and like that, and the quadratic function and its graph, and the cubic function and its graph, given all that, given the above functions and graphs, sketch the graph for each of the following related function. Okay, so in this case, we have f of x equals minus x squared. Well, let's sketch the original f of x equals x squared function. So I'm going to draw this with my pencil, if I can find it here. Yeah. So with my pencil, I'm going to lightly draw the f of x equals x squared function. So it would be something like this. And this would be f of x equals x squared. I'm intentionally drawing this lightly So now let's draw this function, f of x equals minus x squared. So the effect of this minus in front is that it will flip this function or graph across the x-axis. So it'll do that. So this is f of x equals minus x squared. Okay. So let's see this. Let's have a look at the same thing on the computer. So I'm going to switch to the computer. Okay, so we want to graph, let's graph the x squared function. That's that, right? That's the original x quadratic function with no transformation or no shift. But now let's put the negative in front of it. So we're going to say f of x equals minus x squared. Notice how it flipped it. It flipped the original function shown in red across the x-axis. Okay. So let's switch to another example. In the next example, we have another quadratic function. So what this is, compare this with the original general function that we looked at, which was f of x equals x minus k squared, right? So this function stayed x minus something, right? So the k must have been positive 5, which indicates horizontal movement 5 units to the right. So if the original function, and once again I'm going to use my pencil, if this is the original function f of x equals x squared, then this function will have moved that 5 units to the right. So that would be 1, 2, 3, 4, 5. This vertex ends up here. And so that is the graph of f of x equals, or g of x, sorry, that's g of x equals x minus 5 squared. Okay. Are you seeing how this transformation is happening? So let's go back to the computer. I'm going to keep the x squared function up because that's the original function with no transformation. Now we're going to put in x minus 5 squared. You notice? Notice this vertex moved 1, 2, 3, 4, 5 units to the right. Okay, so let's switch back to the dot camera. This one, part C, says x cubed minus, graph x cubed minus 4. Well, first, let's graph just x cubed. So we have the x cubed function. With my pencil, I'm drawing it. It looks something like this. F of x equals x cubed. That's the original cubic function with no transformation. Now this minus 4 means, because it's outside of the x cubed, it means the transformation happens 4 units down. So the whole thing moves 1, 2, 3, 4 units down. Let's draw it. So this point of inflection ends up here, and then we end up with I'm just drawing a rough sketch of the transformation. Whether this line actually intersects the x-axis at that point, I'm not sure. But along the y-axis, yes. This point is negative, the y value at this point is -4. So it was originally at 0, 0. It moves exactly 4 units down along the y-axis. So let's see the same thing on the computer. Okay, so I'm going to change this to cubic function like that, right? So that's what we have for a cubic function without any transformation. Now let's put in our transformed function, which would be x cubed minus 4. Notice how that function shown in red, which was the original function, has now moved. That point of inflection has moved 1, 2, 3, 4 units down. Okay, that's how the transformation works. Okay, let's go back to our dot camera. This is a square root function. So remember from the first page or the second page that the original square root function with no transformation is going to look like this. Okay, let's call that f of x equals square root of x. Right? That's with no transformation. But this is positive 2. So compare that with the original general function for a square root function. So x minus k, right? Compare this with that. That means k must have been what value? Comparing this with that, that means k must have been -2, because minus 2, you end up with x plus 2. So what does that suggest? That suggests that the graph of this function must move the original square root function 2 units horizontally to the left. So this point of origin, 1, 2, moves 2 units, and then we're going to have some graph like that. So f of x equals square root of x plus 2. Okay, so let's go to the computer and plot the same thing on the computer. So I'm going to put in the square root of x, and right, that's that red line that you see. That's the original. It starts right from the origin, and it's a curve-like feature or line going in that direction towards positive infinity along the x-axis. Actually, positive infinity along the x and the y-axis, right? So now let's put in the transformation. The transformation we have is square root of x plus 2. We expect it to move left, right? 2 units there. So now compare that. 1, 2 units to the left. Okay? Like that. All right. So let's go back to the dot camera. Suppose now we have this kind of function which is, it has a minus on the inside, not on the outside. As a matter of fact, let's graph this one and let's graph this one. I should have that also on on the paper too. So let's put another function g of x here and put that as minus square root of x. Okay. So, and let's take h of x, another function, as the original square root function. So we have the original square root function. Then we have g of x, which is the square root function with a minus in front. Then we have f of x, which is the square root function with a minus inside, not in front, but inside the square root. So we want to know how all these two functions transform this original function that we have at the bottom. So I'm going to draw the original function at the bottom here, h of x, right here. So that would be like that. So let's call this h of x equals square root of x, right? So the g of x minus square root of x, this minus in front, do you know what that does? It reflects this function or any function, even the quadratic function. If you have a minus in front of it, it will flip the function across the x-axis. Even an absolute value, it will do that to it. Okay? So the minus in front will flip the graph across the x-axis. So that means for g of x, we have this form. So this is g of x equals minus square root of x. Okay? Then what about this one, when the minus is not in front but inside? If it's inside, the graph is reflected across the y-axis. So if the minus is in front, then the graph gets reflected across the x-axis, like what I've shown, like that one. If the minus is inside, then the graph is reflected across the y-axis, this way. So let's draw that. Something like that. And I'm going to put this as f of x equals square root of minus x. Okay, so let's look at this on a computer, which will no doubt look better. Okay, so we already have the original square root function like that. So we want to first put a negative in front of that. So minus square root of x, right? So minus in front of any function, it will flip the function graph across the x-axis, like this, or reflect the function in the x-axis or across the x-axis. So what happens when we put the minus inside the radical or square root? Minus x. Oops, I should put an equality here, like that. So the green one, you can see that the placing of the minus inside the radical function will flip the original function shown in red across the y-axis, like that. Okay, so let's go back to the document camera. Next, we have an absolute value function. So the absolute value function has the general form like this. Let me just, absolute value of x minus k, right? Compare that with this. And let me draw the basic absolute value function, which has equation y equals absolute value of x. Looks like that. right? So compare this with that. That means k must have been what value? That means k must have been minus 6, because this minus has changed to positive. So that indicates, if k is equal to negative 6, that indicates movement horizontally 6 units to the left. So this vertex would move 1, 2, 3, 4, 5, 6, right there. And then we can draw that the same, like that, and like that. Of course, this is just a basic transformation. I'm not too careful at this point where these lines are crossing. Later on in the course, we will draw more precise graphs. But at this point, I just want to show you how transformations work graphically. But if I had done a better job, then that line would have crossed the 6, where the y-axis is at 6. Okay? But at this point, I want to show you that this vertex, this means the vertex here moves 6 units to the left, and this is why, because k is negative 6. Okay? So we can also look at this on the computer. So let's put in the absolute value function. Absolute value of x has that graph, right? We know that. The vertex is at the origin, and the arms of the graph have a V-shaped form like that. Now, let's put in what we the example that we have. Let's call it function g of x equals absolute value of x plus 6. So we already know the movement is going to be to the left 6 units, right? Like that. So compare that. The vertex here moved 2, 4, 6 units to the left. Okay, so let's go back to the dot camera here. Oh, so we now, very nice, we reached the piecewise functions. These are very cool. So let's see, we're going to go through a couple of exercises to see how we can graph these. Okay, so here, let me just basically say what we will be doing. Piecewise functions are conditional functions. In other words, depending on the value of x, the function has a different value. In this case, we know that if x is equal to or something equal to or less than -1, then the function will always be 8. If x value is something greater than -1, then the function will always be x squared. When you're asked to draw a piecewise function, never worry about the conditions. Never worry about the conditions. Just like that, imagine that they don't exist. Then, very lightly, with a pencil, never a pen, draw each piece of the function as if it was the only piece. Draw both with a pencil, very lightly. Once you've done that, then you take a look at the conditions and you erase part of the graph that you should, and you keep the one that you need. Okay, so what do I mean? Here's what I mean. For now, we're going to assume that these conditions don't exist. So this function is going to be 8, it's going to be x squared. So I'm going to draw both of those with my pencil very lightly, because that's not the final graph of this piecewise function. Very lightly, I'm going to draw f of x equals 8. So let me do that. F of x equals 8, that means a horizontal line that goes through y equals 8. So I'm going to draw it very lightly. see, you barely see it, right, on the screen. And then f of x, I'm going to draw f of x equals x squared, once again with my pencil and very lightly. So here's how I'm going to draw this. Very lightly, like that. Okay, so we ignored the conditions. We drew each piece of the function fully without regards to these conditions. Okay, so now you have a rough idea about both pieces. And I should grab my eraser if I brought it in order to erase. Yes, I do. I have my eraser with me. So there it is, my eraser. And we're going to have to erase the piece that we should erase, that is not relevant to this function. So now let's take a look at the function conditions. If x is less than or equal to -1, x equals to or less than equal to -1 is right here, right? So if that's the case, then the function is equal to 8. So if we're here, and equality is allowed, so I'm going to put a filled-in circle here, right on top of 8, and I'm going to draw with bright color that piece of the graph that I know is accurate, like that. So if x equals -1, then the function value is always 8, like that. That means I have to erase the rest of this all the way to x equals -1, because none of that matters anymore. So this is not going to matter, right? That's not going to matter. All of this curve, we don't need that. All the way to -1, I erased everything. All right, maybe I should clean it a little more, like that. So now what? Well, take a look at the next condition. It says once x is greater than -1, so I'm going to not equal to -1, right? So I'm going to put a hollow circle down here over -1. Greater than -1, the function is equal to x squared. So that curve, it's going to be the rest of the graph. So I'm going to erase everything else, that horizontal line, which continues on the other side, like that. And I'm going to darken this piece. Like that. And that's the graph of that piecewise function. So like I said, when you begin graphing any piecewise function, just ignore the conditions, lightly with a pencil, draw both pieces fully with no restriction, as if they were the only piece of the function. So y equals 8, draw it fully. Y equals x squared, draw it fully. Once you draw each piece fully, then you go back and erase the pieces according to these conditions. Okay? All right, so let's see another example. Here we have another piecewise function, right? Just like before, ignore those conditions that you see, f. Those are conditions. Ignore them. Imagine they don't even exist. And then draw each piece fully. F of x equals 4, draw it fully. F of x equals x squared, draw it fully. F of x equals -x plus 6, draw it fully. And then start erasing by looking at these conditions. So let's do that. So the easiest piece is f of x equals 4, right? So let's draw that. F of x equals 4 means there's a horizontal line going through y equals 4. There. So you can see that I drew it very lightly. Right? F of x equals 4. Then let's draw the f of x equals x squared part very lightly. So I'm going to do my best to draw it like this, going through the origin and coming up like that. It's a parabola, right? So here we have two pieces drawn fully without regards to the conditions, and we have left with that. That's a linear piece, linear equation, right? F of x equals minus x plus 6. It's a straight line. So let's identify where the x and y intercepts are for that one. I'm going to do it here. For f of x equals minus x plus 6, for that, if x equals 0, then y or f of x equals 6. So we have 0 comma 6 as the y-intercept. If y equals 0 or f of x equals 0, then we have 0 equals minus x plus 6, or x equals 6. So we end up with 6 comma 0 as the x-intercept. So let's plot these 2 points. Let's plot 0 comma 6 and 6 comma 0. And very lightly, right, with a pencil. So 0 comma 6 would be here. And 6 comma 0, let's see, did I? That is correct. Y equals 6. So like that. Okay, that's 6 comma 0. 6 comma 0 right there. So now, with it, just draw a line very lightly through those 2 points. Like that. So now, you have drawn all 3 pieces, f of x equals 4, f of x equals x squared, f of x equals minus x plus 6, very lightly on a piece of paper. Now, here comes my eraser, right? I need to go through and look at each condition and erase the piece that is not needed. Let's do that. So, f of x for any x value less than negative 2. Less than negative 2, the function value is 4. So that means less than negative 2, not equal to negative 2, right? So I'm going to put a hollow circle right above x equals negative 2. And the graph should be this piece. Like that. So this curve should be erased all the way down to where we have negative 2, right there. Okay, so let me do that. So I'll try to make this red line a little bolder, like that, maybe a little darker, like that. Okay, so up to x equals x less than negative 2, we have this line. Function value is equal to 4. What happens after negative 2? At -2, when x equals to -2 or equals to 2, between those two values, the function is the quadratic function. So that means I'm going to put a filled in circle here, because x at that point along this function can be equal to -2. So a filled in circle. Then I'm going to darken all the way to 2, which is right there. Which actually, if I drew my graph better, it should have been right there. So, because the graph of the f of x equals x squared is symmetric. So let me put a circle right there on top of 2, and then the line, the graph of the piecewise function, would be like that. Okay, that piece. And at those endpoints, x can be equal to 2 and can be equal to -2. So I'm going to erase the rest of this curve. Like that. Okay. So what happens after 2? Beyond x equals 2, the function is equal to this straight line, which we've already drawn fully. So beyond 2, that means greater than 2, right there, we put a hollow circle, because along this function, x cannot be equal to 2. So I'm going to put a hollow circle there, and I'm going to complete the rest of this graph. Like that. Like that. So that means I'm going to erase that piece as well. All of that doesn't matter. Okay. So this is the graph. This is the graph of that piecewise function that you see. And also, let me erase that horizontal line too. All of that should be gone. And that piece. Okay. I hope this makes it easier for you to see or to know how best to draw the graph of a piecewise function. With that, we have wrapped up, or we have concluded section 2.2. As usual, thank you for persisting through this video, and I have a nice day for now, and I'll see you next time.